Welcome to this session for our 5th Monday. And this follows on from my talk about 2 weeks ago, where I was looking at characterising heavily contaminated urban sites. And then, of course, last week we had some really lovely field experiments looking at other types of contaminated sites. But for today, I'm going to take us back to the laboratory. That's going to be my starting point. And I'm going to be talking about the steps that we took to design and then to test a remediation method for our very heavily contaminated high pH chromium-6 sites in Glasgow. So I'm aware that maybe not everyone was able to access the lecture 2 weeks ago, so I'm going to give a very quick recap of the problem that we faced. So in Glasgow, due to historical contamination from a chromium chemicals work, we generated about 2.5 million tonnes of very high pH chromite ore processing residue, and a large amount of this was deposited in landfill sites in southeast Glasgow. Now, the chemical company closed in the late 1960s, and so the last of this waste material was probably deposited 40, 50 years ago, but we still have chromium-6, the hexavalent chromium, highly carcinogenic chromium leaching out even to the current time. And from our initial work, we were observing very high concentrations of chromium-6 in the groundwaters, as an example here, up to about 125 mg per litre in this initial work. And the pH of these waters was up to about 12.5. Now, there was a lot of public concern through the 1990s into the 2000s about the chromium contamination and then the effects of that on human health. And there were indeed some health studies done, but it wasn't possible to directly link the chromium contamination to the cancer cases that were observed in this area of South East Glasgow. Nevertheless, though, the public put a lot of pressure on the councils in Glasgow and in the surrounding area to do something about these sites. And specifically this area here, which is called the Shawfield site, which takes in the chemical works and many of the areas of landfill that have the chromium waste. These are then shown on this map to the right here, and we are showing the concentration of hexavalent chromium. The large dots show where the concentrations are greater than 200 milligrams per kilogram, and the shading tells you the depth of that contamination. So some of it in excess of 10 metres depth, so quite a difficult thing to remediate. So the councils had quite a big problem on their hands, with 15 sites being identified where the Chrome-6 contamination was at depths of greater than 10 metres. These were the sites that were being then targeted to clean up. Many of the off-the-shelf methods for remediation are based around the properties of chromium, hexavalent chromium being reduced to chromium-3. The reasons why that is favoured is because the chromium-3 is generally perceived to be less toxic, and also it tends to be removed from solution to the solid phase, either by adsorption or by precipitation of various hydroxide phases. In addition, there are very few processes that occur that will reconvert the chromium-3 to chromium-6. And in our favour at these sites, because of the high pH, is the very low rate of reaction of that reconversion. So that's why the methods tend to favour the reduction to Chrome-3 as the best approach for reducing the risk of these sites. So these are some of the typical reducing agents that have been considered, and there's a whole body of work from Glasgow site, many consultancy reports as well as peer-reviewed published literature. And just gathering together that information, we were able to see that the main electron donors were reduced sulfur compounds, so sulfide and dithionite, reduced iron, the zero variant iron and iron 2, and a whole range of organic compounds, including natural organic matter and molasses, lactic acid and things like that. On this slide, I'm just showing the reaction for iron 2, so it's just one of the examples. So there you have the hexavalent chromium being in first instance converted to chromium 3, whilst iron 2 is converted to iron 3. And then the second part of the process is a hydrolysis and precipitation state. So in this case, we have a mixed hydroxide being formed, iron chromium hydroxide, and the proportions depend on how much of the reactants that you have in that mixture. So that's one of the possible processes, but as I said, there were many tests done at these sites, and in the main, they were not very effective at reducing chromium-6 at what we call these high Lyme or high pH contaminated sites. And the reasons for that is, one, it's quite difficult to get the reagents in contact with the material. It's a low moisture content material, and it often has a very hard crust on the surface, and that limited the effectiveness of biological processes, microbial processes, as well as the chemical processes. So that was the general picture at the time from other people's studies, but just to illustrate, we did some laboratory experiments ourselves, and these involve column experiments where we took the COPR material and passed through it iron 2 solutions, just to show what's happening here. So we have the orange control line here. So that's the control column, and then there are two different treatments. There's a brown one, which is the iron chloride solution, and there's a red one, which is an iron sulfate solution. So for the control, this is what we were expecting to happen. The chromium-6 just continues to leach out no matter how much of the solution as 1 millimolar sodium chloride electrolyte solution being passed through it. And that's consistent with what's going on in the environment, this continued leaching over decades. And then when we look at the iron chloride, we don't see any reduction, perhaps a very tiny amount of reduction in the very, very early stage just here, and then thereafter very little difference between the iron chloride column and the control column. So in essence, what was happening was that the iron 2 was being oxidized before it reached the chromium-6. So we got the precipitation of iron hydroxide, and the chromium was just free to leach out as before. When we tried iron sulfate, which we picked this because it was another commonly used method, we got a bit of a surprise, and in actual fact what we found was a very large amount of chromium coming out the column, and it was all chromium-6. So we were in some ways making the problem a lot worse, because we were leaching out this extra chromium-6 from the material. So what we concluded was that sulfate was increasing the release of chromium-6, and we looked to the structure of the chromium-6 containing minerals to try to understand what was going on here. So for those of you who listened to my lecture 2 weeks ago, I showed the structures of two of the main chrome-6 phases. Here on the left, that's the one we're going to focus on, which is the hydrocalumite, which is the kind of inside-out clay with the spaces in between the layers, in which we have the chromate ions. So we hypothesized that sulfate could displace the chromate. And we then went to the scanning electron microscopy with the EDX option to get elemental analysis to see if we could actually prove that this was happening. So these are thin sections of the material, and we did a before and after treatment. And very nicely, we had the hydrocalumite layer here shown, and then when we looked at the elemental analysis, the before and then the after treatment, what we could see was that there's before, so we've got lots of chromium. The chromium goes down and the sulfur goes up. So good evidence to show that our mechanism is correct. So we've got an ion exchange process going on here. So you might think that, well, we could use this as a kind of leach and treat. And if we had very good control over where our leachate ended up, then perhaps this would be an option. That you could take some material and use the iron sulfate, not for its intended purpose, which was the reduction of chromium-6, but to take out the chromium-6 and then to treat the liquid elsewhere. However, I think in the scenarios that we have, especially knowing a bit about the hydrology and the geology of Glasgow, we don't really have good understanding of where the leachate ends up. So we decided this was not really the best option. So for the purposes of our work, we looked to alternatives, and this suggestion came to us from a consultancy that we were working with, URS, and Dr. Richard Bewley had been doing some investigations of studies in the US, and he'd picked up from their literature that calcium polysulfide might be an alternative, and I think it was used for a metal plating site, and there were some encouraging results. And this was the proposed reaction of the chromate being converted to chromium-3, and again the hydrolysis and the precipitation giving us the chromium hydroxide solid phase. And this polysulfide, represented here as S5, was converted to sulfur solid. So these were the initial reports, and the reports also suggested that calcium polysulfide was more stable and more persistent in subsurface environments. So that was what made us think about this as an alternative. So at the start of this project, we had to buy some polysulfide from somewhere. I think we initially thought in making it, but we quickly decided against that, and we purchased some, but you need to know what it is that you're working with. So we did a bit of reading and some early chemistry textbooks, sort of 1900s to 1950s books we were looking at, and we found this recipe for the production of polysulfides. So it's what they call milk of lime in these old books, which is essentially calcium hydroxide in water, and you boil that up with some elemental sulfur, and you produce this very deep orange red, highly alkaline solution, which fumes and bubbles. So it almost looks like something that you might find in an alchemist's workshop rather than our own laboratories. But in essence, we produce the first form products are thought to be the S4, which is I've just represented here. And then also we produce some thiosulfate. So that's the first form products. But there's quite a lot of chemistry going on in these solutions. Sulfur chemistry is quite complicated, and we know that the thiosulfate decomposes to give sulfite and elemental sulfur. We also know that the S4 polysulfide disproportionates to give S5 2-, and that's why this is often the one that's represented in the chemical equation if you see that for the representation of calcium polysulfide reacting with the chromium-6. But you also generate HS-. So there's a lot of sulfur species dissolved, and there's another one that comes into it because the elemental sulfur that I showed you being produced here is actually quite soluble in the polysulfide solutions. So it's not forming a solid phase. Quite a lot of it can dissolve up. And so that means that you cannot use the concentration of sulfur to represent active sulfur, the active sulfur being the bit that will react with the chromate. So we got round this by using the calcium concentration. So we know we must have a charge balance. We measured the calcium concentration, and then we made the assumption that that would be balanced by active sulfur. It does make a big difference because then we have 2.15 molar active sulfur and not 39.1 molar, which is what we would have based on total sulfur. So there's a lot of things to do just to start off with before we can actually test how our treatment is going to work. So the next experiment we did was to look at the stoichiometry reaction. We had what we thought was the active sulfur concentration, and then we made up a range of polysulfide solutions by diluting the procured solution. And then we made a range of chromium-6 concentrations, and that's all the concentrations converted to millimolar down the side. So then that corresponds to about 6 up to 134 milligrams per litre of chrome-6. What we were doing here was looking at the minimum concentration of polysulfide to effect the complete reduction of chrome-6. And what we meant by complete was taking it to below detectable limits of 0.01 mg per litre. So we did this for the range of chromium-6. I'm just showing you 3 examples here for the pink, the blue, and the green lines. And we got a stoichiometry, chrome-6 to polysulfide of about 1.65. Now, based on the equation up here, it should be about 1 to 1.5. Given the experimental error and that we haven't got every single point along here, we've only got selected points, this shows very good agreement. And so we were quite confident that the process was working according to the stoichiometry shown in the slide here. We modelled the process too. So just showing you again what the ORCHESTRA model can do. So it's a framework that you then put in various processes, like we've got the dissociation of the chrome-6 acids, the reduction process that we want to effect using the polysulfide. We need hydrolysis of chrome-3, and then precipitation of the solids, the chromium hydroxide, also the sulfur solids, and various other processes that go into the model. We put in the initial chromium-6 concentrations and the calcium polysulfide chrome concentration too. And this just shows you the output, so the general picture coming out very, very similar. And indeed, we got very good agreement with the between the modelled and the observed stoichiometry. Importantly, the model also predicts that chromium hydroxide and elemental sulfur should precipitate. When we did the actual experiments, we did see a grey-white precipitate. Now, we can't really analyse this using the X-ray diffraction because it's an amorphous precipitate, but what we can do is digest it and get a mass balance. So that's how we went about just checking that we had our chromium remaining after the experiment. So we had our initial mass of chromium, what was remaining in solution, what was in the precipitate, adding the solution and the precipitate together to get total recovered. You can see that we've got a fairly good mass balance, 97.2%. So all going really well. If we're going to use this type of reaction, we need to know how quickly it happens. Now, we did observe the precipitate happening, forming almost instantaneously, so we did suspect it was a very quick reaction. And if you do the timed experiments. We took one of the chrom-6 solutions and an excess of calcium polysulfide. The reaction follows pseudo first order kinetics, so you can get the slope here, and a reaction half-life of about 9 minutes. In terms of the experiment, you can see just being shown there to 50 minutes, no detectable chrom-6 beyond about an hour. So a fast reaction. Obviously, this is in just looking at solution phase, but very encouraging and allowing us to move on to the next step. So we've been working with potassium chromate. So we need now to then look at real water samples because they have many more things in them. How do we know that the calcium polysulfide solution will do the job when it's put in contact with real samples? So we went and did some borehole water sampling in the vicinity of the contaminated sites in Glasgow. Of the ones we collected, only 2 had detectable chromium concentrations in the solution, so I'm just going to focus on them. One of them was just behind the football terracing, which I showed you earlier, one of our favourite sites. So it's just, there's a sample over here, there's a football ground. And the other one was on waste ground that was near the original chrome chemical works. These are what the samples look like. So that's the one from the chrome chemical works, and this one is the one from behind the football ground, looking very different. The one from the chemical works, really, really high concentrations of total chromium, and most of that was chrome-6. Now, I have to say, to my shame, that I made my postdoc repeat these measurements several times because I couldn't believe how high they were, but he was absolutely right. These are the concentrations of chromium-6 in that solution, the highest that we've ever measured. But very good then to test out our method. The other one mainly has chromium-3, a very, very high pH, pH 12.5, and this shows you what happens when the leachates from these sites move through a normal soil with organic matter in it. So the organic matter is dissolved up and is causing this coloration of the groundwater, where you can see that there's quite high concentrations of chromium. Although chromium-3 is much less toxic, it's still an issue. So we kept the sample as part of our set. I did a little bit further characterization work. I'm not going to say too much about this. The yellow solution, as expected, is truly dissolved chrom-6. We just wanted to show that the chromium in the brown coloured waters was actually associated with the organic matter. So we did a first step of ultrafiltration. Most of the organics are in the large colloid fraction, and that's where the vast majority of the chromium was as well. Gel electrophoresis showed that they co-migrated, the organic matter and the chromium-3 co-migrated, so we were fairly confident this is chromium-3 organic complexes here. So to the treatment, well, I diluted the very yellow groundwater from the chrome works in order that we could get sensible concentrations of the polysulfide. So that's why I've diluted by 2 here. So these are now my starting points. And then you can see that for all the treated solutions, even where it's just a 1 to 2.7 ratio, there's no chromium-6 remaining in solution after 4 hours. This is what we would expect, but there's nothing else interfering with the process. So that works extremely well. Interestingly, for my organic-y solution, which didn't have a lot of chromium-6, it was mainly chrome-3, there's no chromium remaining in solution after we expose it to calcium polysulfide. And this is because of the amount of calcium and just the increase in the ionic strength of solution, which makes the organic colloids unstable. And so we observed a brown sludge forming at the bottom of the reaction vessel. And hence, we have a treatment that actually works for both types of solution. But the main interest is obviously the chromium-6 ones, because that's where the risk is. So solutions are easy to treat. There's no problem there. The big problem is these 10 metre, 12 metre deep COPR contaminated sites. And this is the real challenge. We needed to know that the method worked first in solutions, but now we move to applying it to real solid phase samples. So this is the JCB excavation of one of the football grounds, a different one from what I've shown you before. Here's our postdoc collecting the samples, and there's just a profile of one of the pits. So we took 3 trial pits around the place, but this one was our favourite one because it had really nicely defined layers, and they turned out to have quite contrasting levels of chromium-6 in them. So they looked different. We've got a top layer that's light brown, crusty, with some yellow nodules. Then we had a beautiful, softer yellow-green material, and then a transition to a grey material with yellow lumps. And so you can see very high concentrations of chrome-6, but layer 3 in the middle was the one with the highest values. We undertook the X-ray diffraction, and we had the same minerals present as for the previous COPR sites. So we have chromo-3 phases, the chromite, unreacted chromite and brown millerite. We have periclase, brucite, calcite coming from the reagents that were used in the roasting process. And then the 2 that I've highlighted in yellow, which are the hydrogarnet and the hydrocalumite. And the main one was the hydrogarnet, and you can see that there's a reasonable correlation between the chrome-6 content, that was the highest one in the previous slide, and the hydrogarnet content here. So that's the material we're working with, and then we're looking at how it reacts with the calcium polysulfide. Can calcium polysulfide work where many of these other treatments have failed? So we did a series of batch experiments. So these were 4-day experiments involving shaking of the COPR material with an amount of calcium polysulfide with an extent of pH adjustment. So we have, and I'll show you just on the left-hand side, we have the aqueous phase. So this is what is remaining in solution after treatment. And on the right-hand side, we have the residue that's then been reacted and the chromium-6 concentration determined afterwards. So just looking at the solution, we have the untreated, then we have a 1-to-1 treatment, and we have a 5-to-1 treatment. And we're going from high pH to low pH. So looking at the control, so that's a zero treatment here. This is the same as what I showed in the last lecture, where we start off with low chromium-6 concentrations in solution, and then as we start to dissolve up the matrix, we release chromium-6 into the solution. So you get the highest values at the lowest pH that we've used here, which is pH 8. When we go to the 1-to-1 treatment, we can see that we have the same trend, but to a lesser extent. And by the time we get to the 5-to-1 treatment, there is no detectable chrome-6 at any pH in solution. And this one is for layer 3. That was the one that had the highest chromium-6 concentrations. If we look at the comparable solid phase, you can see for the control, we had the high values at the high pH, and then we know that we're dissolving up the material, so the chromium-6 concentration remaining in the solid phase does decrease a little bit. For the treated samples, there was no detected chromium-6 either for the 1-to-1 or the 5-to-1. And that pattern was repeated for the other layers. So you can see layer 2, layer 3, and layer 4. So very encouraging indeed. We try to model the process. So I showed you model results in the last lecture, and so typically what I was showing was, and if we're looking at the top one here as the untreated, so this is just the material, as we changed the pH, what we observed was the increasing amount of Chrome-6 in solution as we decrease the pH. So the model again shows that trend, and I've put the experimental results on the left-hand side. So we're going from high pH down to low pH here. So if you look at the big picture, the model does predict the same pattern. And so when we go from no treatment through 1:1 to 5:1, we have a general decrease in Chrome-6 to eventually non-detected chromium-6 in solution. And the concentrations are within magnitude about the same, especially for the middle layer. It's a bit too high for layer 2. But the big picture is there, and the model does predict precipitation of chromium hydroxide and elemental sulfur. I think probably one of the reasons why the model isn't as good as we would like it here is because although we use the solution phase chemistry based on the work that I've just been showing today, it was the previously published solid phase data rather than the specific solid phase data for these samples. So I think a note of caution about models is that they're only as good as the data that you put into them, and so there is certainly a limitation there if we're looking at the fine detail of what's going on around about pH 9 to 11. But our main purpose was to investigate the reduction of chromium-6 to chrome-3. We've clearly removed it from solution, and we're not detecting it in the solid phase. So the next thing to do was to look at what was left in the solid phase. So we looked only at selected samples. And this slide looks quite complicated, but what I'm showing is only 2 pH values, so about pH 12, so that's at the high end, and at the low end pH 8 for the control, for the 1:1 treatment, and for the 5:1 treatment. And we have the 2 chromium-6 containing minerals, the hydrogarnet and the hydrocalumite. So the general trend, for example, if we are looking at hydrocalumite and the green highlighted samples, you can see as we go from 0 to 1:1 to 5:1, as there is a decrease in hydrocalumite. The biggest change we observed was upon change of pH, and that was for the hydrogarnet. So we can see a major lowering of the amount of hydrogarnet consistent with a dissolution process. So we know that the calcium polysulfide is very effective in reducing the chrome-6 to chrome-3. Now, the quantitative changes in the mineral composition were maybe just a little bit lower than we'd anticipated, but if we looked more closely, we could see that there were some changes, and I'm focusing in on the hydrocalumite here to try and get at the mechanism of what was going on. So we did see some what looks like dissolution, but we also saw a change in the interlayer spacing within the hydrocalumite. So that was the inside-out clay with the layers. And so that change in interlayer spacing pointed towards an anion exchange process. So possibly we're looking at a 2-step reaction where we have a release into solution followed by reduction. And I've tried to show this on this slide here, what we think could be going on in solution. So in the middle, we have the hydrocalumite structure, a part of it, with the chromate in the interlayers. So we think there's some ion exchange process that is releasing chromate into solution. And then we have the polysulfide, which, when it comes into contact with water, it can decompose or dissociate, and we end up with a hydrogen sulfide. And given the pH of solution, it's most likely that that will dissociate to give sulfide ions. So these can cause the transformation of iron 3 to iron 2. So we could invoke iron 2 as a potential reductant for the chromate. We can also have polysulfide itself and the sulfide ion all doing the business and converting chrome 6 to chrome 3. So these are some of the things that we think are going on, and some of the reasons why the polysulfide is so good at treating this solid material. The hydrogarnet, as I said, acidification lowers its concentration significantly. We don't know as much about what's going on here, but we think dissolution followed by reduction is a big part of it. But because we don't determine any chromium-6 remaining in detected and in the residual solids, then again an ion exchange process might also be important here, releasing the chromium-6 into solution. And we know that that's how the hydrogarnet formed in the first place, with the chromate substituted into its ion exchanged into its structure. So that wouldn't be inconsistent with what we know about hydrogarnet, but we don't have as much evidence about the behaviour of hydrogarnet. So far we have a reasonably good understanding of what's going on with the chromium, but in terms of letting us use the method, we also need to understand what's happening with the sulfur, because one of the concerns of the consultants and indeed the engineers that we were going to be working with when it comes to using this method in the field was they were very worried about the forms of sulfur, especially the generation of hydrogen sulfide gas. Because if you've got HS minus in solution and the pH drops a bit, then there's a potential to generate H2S, which could then be released and pose a risk to human health. So if we looked at the sulfur phases within the residuals after the polysulfide treatment, and for 9 out of the 12 treated samples, we detected elemental sulfur. So that was very encouraging. So in terms of the length of time of our experiments, the oxidation of sulfur was stopping at that stage, but we were getting a solid precipitate. We suspect that over time, sulfate will be likely to form. We did observe some sulfate for the low pH samples from the near surface. That was the layer 2 of our pit. And we think that is because of dissolution of calcium-containing species and the subsequent precipitation with sulfate. And some of that we think might have been atmospheric deposition of sulfate from the near surface material. So we have these two forms of solid phase sulfur, very encouraging at this stage. Batch experiments, however, are not a good representation of what would actually be going on in the field, because we can't necessarily mix up tiny amounts of material with lots of liquid to get the good results and the reproducible results that I've shown you so far. So the next step was to use a column experiment. And this just shows the makeup of our column here. So we've got sand, then we've got the COPR material, and we pump liquid up from the bottom to avoid compaction. Two types of column. We have a control column, which is simply pumped with 1 millimolar sodium chloride as our background electrolyte, and a treatment column where we move an amount of calcium polysulfide solution onto the column, let it equilibrate for 20 hours, and then move to the 1 millimolar sodium chloride pumped at 6 mils per hour. Thereafter, total length of time for the experiment, 145 hours. So I'm showing you the actual results for a reason here. We actually got the column volume slightly wrong, I have to say. We thought our column volume was about 10 mils, and in actual fact it was 14 mils. And so what happens in that case is that you have some unreacted material at the top of the column. And so when we started to pump the sodium chloride through it, then we got the release of some chromium-6. So the top line here is the control. So again, showing you high concentrations at the beginning, but then continuous leaching. I'm only showing the first 20 hours, but this goes on for 145 hours. For the treated column, we have high chromium-6 coming from this unreacted material over the first 2 hours, and thereafter we had no detected chrom-6, so less than 0.01 mg per litre again. I'm showing also just the treated column data for calcium and sulfur, and showing that as the chromium-6 concentrations dropped to non-detected, the calcium and sulfur concentrations increased. The pH, first of all, increased just round about here. We had an increase to about 12.8, and then the pH decreased to about 12, so it came back to the same as the control. And this is consistent with the consumption of protons that is shown in the reaction stoichiometry. So we were fairly confident that the process was working, and that these results suggested that the reduction had gone to completion. We took out the column material and analysed it afterwards, compared it with the before. So here's the before, the very high concentration material is what we used. So you can see for the control, there's a lot of chromium-6 remaining, and this is the total amount that was leached. Most of that was chromium-6 for the control column. Quite a significant contrast with the treated column. So we've gone down to about 53 milligrams per kilogram. So even with that slight error in our calculation of the column volume, we had more than 99% reduction of chrom-6 in the column solid phase experiment. So very, very good. The leachate, 93% reduction, that initial amount was because of that non-reaction of the material. Very importantly, there was a tiny amount, less of something like 0.4% of the total chromium was lost from the column. So pretty much everything is staying in the solid phase. We couldn't identify the chromium-3 phases present, and we didn't really pick up any mineralogical differences when we looked at the column material. But we were confident that because the chemical modelling was giving a strong indication of the conversion to chrom-3, we're detecting very little chrom-6 in our column residues, chrom-3 is being retained in the solid phase, and also we didn't really observe any change in the column permeability over the 145 hours, that we could then move on to some nice field experiments. Now, in first instance, these were not direct applications to the material here as you're seeing it in the environment. We excavated this material about 40 cubic meters and put it in skips. So these are like enormous batch experiments with 3 meter cubed per skip, and adding 300 liters of calcium polysulfide per skip. Now I have to say, this is the before, so this is all you see how heavily contaminated this material is. And these had to be mixed by the JCB, and after the reaction was complete, we were very pleased that we got results that were really strongly comparable to those we got in the laboratory. So very high levels of reduction of chrom-6 in the leachate and non-detected in the solid phase. We know that we're forming new solid phases. We demonstrated that in the lab, and one of the things that the engineers came back to us with is that if you're going to generate large volumes of new solid phases, then that might be a problem, what the engineers called heave. But we got no significant change in the volume of the solid phases in the skip, and we also didn't get any detectable hydrogen sulfide gas. So that allowed us to move on to the final stage, which was treatment in the field. And I'm not really going to say very much about that because the main purpose of today was to show you the development of the method. But just to let you know that it was successful, we tried 3 different ways of applying the calcium polysulfide in the field. There was a recirculation experiment where the solution of calcium polysulfide was pumped into the ground and then recovered and recycled multiple times. There was another experiment in a different part of our site where a 5 by 5 meter area was excavated a little bit and mixed with the calcium polysulfide material. And then there was a direct injection method, which was in this part of the site, where a 10-meter long injection pipe with holes in it at every 20 centimetres was placed into the ground, and the solution was released at about every 20 centimetres down to 10 metres depth. Just summarising the results here. So the least effective method was the groundwater circulation. It still achieved a good extent of reduction. The chromium-6 in groundwater would be satisfactory. The aim at this site was to get it less than 500 because an on-site of less than 500 micrograms per litre would give an off-site value of less than about 20, 30 micrograms per litre, and that was the target for this remediation process. The downsides, we got precipitates near the well interface and preferential flow channels, so didn't really like this method. The soil mixing means you have to have full site access, and we did find unreacted chrome-6 nodules when we examined the material, but in general quite good results. Our favourite one though was the direct injection because the on-site chrome-6 concentrations were less than 30 micrograms per litre. You don't need, it's not so invasive, and we got the less than 1% solid phase chrome-6 remaining. So all methods could be used, but I think the general feeling of our team was that direct injection was the most versatile method and presented a solution to a long-term problem in Glasgow. So my final slide is just to show you that method has been successful for the site here. Cost something like £2.5 million to just buy the reagent. In the grand scheme of things, though, it's a £400 million regeneration project, which is likely to generate a lot of jobs in the area. It's now, I think, in its 2nd to 3rd phase, and so this is a kind of simulation of the site, but many of the buildings are now in place, and businesses are moving into the area. So my overall message is that to develop a remediation method, you need to first of all understand the material that you're going to treat, and then you also need to know about the reagent that you're going to use, how it behaves in the laboratory. There's a lot of testing that has to be done before you can go to environmental application, first of all in controlled scale, such as the SCIP trials that I'm showing here, and then in the full-scale implementation. So thank you very much. I shall now let go of my screen, and I will take any questions if you would like to ask. Okay.
I'll fire one in then. Your end sulfur product, you said, is elemental sulfur, is that right?
Yes.
So does that mean you're storing up elemental sulfur in a site which over time will oxidize, producing sulfuric acid, which is then going to leach out more chromium?
We think that it will transform to calcium sulfate. The end pH that we observed was still very, very high at these sites. So the pH was still sitting at 12. So we think that sulfate is likely to be the final sulfur product. Obviously, if the pH were to come down, then that might be an issue. You could change the sulfur speciation, but even when we've put about 4 years of Glasgow rainwater through this material, the pH doesn't come down below 11. So we think it's unlikely, unless there was some major process where mineral acid was added in great excess to the site, that you would generate the sulfuric acid speciation of sulfur. Does that answer your question?
Yeah, I'll take that.
Yep.
Maybe along that same line, and I apologize because my internet's a bit wonky and I lost you for a minute there when Ian was asking his question. But is there any set of circumstances under which you could envisage reoxidation of the chromium once it's been treated?
Well, if there was a lot of manganese there, that would be your main sort of environmental oxidant. But because the pH is staying very high, we suspect that on this site that is not likely, because the rate of manganese transformation of the chrome 3 to chrome 6 is extremely slow beyond about pH 4. If this material is transferred, like so if the actual material washes off the site, we don't know exactly what's happening in the Polmadie Burn, which is not too distant. It's a site that one of my PhD students is working on. And it then maybe gets deposited in banking soils. So we wonder if there might be the potential there for oxidation processes, and that's what Gavin is working on in his PhD at the moment. What might happen to that material if it moves off site, so if the solid material were to move off site. But on that site, because of the very high pH, I'm not aware of a reoxidation mechanism.
That would also be my question, but I have another question. In the beginning, you said something about the iron chloride and iron sulfate column experiments, and you said that the sulfate was exchanging chromate, so mobilized. But then I lost you. What was really the purpose of this experiment? I mean, you wanted to stabilize and not mobilize.
Yeah, the purpose of the experiment was to use the iron 2, but the iron 2 was just precipitating out as iron 3, so it never got in contact with the chrome 6. Okay. Some people were suggesting that we could use a sulfate to flush out the chromate, and then you could perhaps take the leachate and treat it elsewhere. So under controlled conditions, where your standard remediation methods might work a bit better. But we felt that for a site in Glasgow where we don't understand the hydrogeology of the site, and that some of this waste material is at 10 meters depth, then it is not really a very good strategy to be adding something that will enhance the chromate, which may then end up in the River Clyde or other surface waters.
So you abandoned that approach?
Yeah.
Okay.
Yeah.
The chromium in your waste seemed to be almost at percentage level. Was there any attempt to recover it, to mine it out?
No, I wonder if there was some reworking of one of the disposal sites at the time, but it's certainly not after the chromium works ceased in the 1960s. So some of the material is under the surface, some of it's under buildings, so a lot of it's actually quite inaccessible. And that again is the problem about remediating it. We have very inaccessible sites, and why we came down to the favouring of the direct injection, because even on the Schenken site there was a layer of concrete on the surface, and digging all that up first before you can get an access with the waste it's quite a difficult and expensive challenge. I think there is, I mean, certainly some, you know, we see layers of the material, and one of the things I think Doug had asked me about on my previous talk was about these the brown millerite rims around the material, and when we look at layers 2, 3, and 4 at that site, I don't know whether this relates to waste that's been put in at different times, or whether there had been some attempt to change the material. But I did notice when I was looking at our data again that when you compare layers 2, 3, and 4, that there is a change in the brown millerite content. So the near surface material has much less brown millerite, and I wonder perhaps if this is a weathering process, that's evidence of there starting to be some change. So that was it's just really an aside for answering a question that came up about well in my previous lecture. But we really don't know exactly what's happening, or what happened to this waste material, and whether there had been any attempt to recover chromium from it. I see there's another question here. Are there other similarly contaminated sites at which this remediation method could be applied, or are the characteristics of the Glasgow site unique? Yeah, well, there certainly in New Jersey, there is the similar type of waste material, and there is a research group, Tang, I think, and Kurzoku, who have applied our treatment method at the site and have had some success in using it. I think there's quite a number of applications around the world, and there are some things to watch out for, though, because the nature of the waste material can change. So, for example, in New Jersey, they have a lot more ettringite, so their waste material might behave in a slightly different way. Although, when you think about ettringite, it does have the chromate and anion exchange sites, and I think so you might invoke similar processes. I read a paper recently on Indian COPR, and because of the hydrological conditions there with the monsoons, they again have a different type of waste material to treat. So there may still need to be some examination of the waste material and how this type of remediation works to make sure that it is as effective at treating other sites. So Glasgow is not entirely unique. There are other locations in the world, but just with some caution that the mineralogy can be different, maybe in part due to changes in the process, but also due to the hydrological and other conditions that the waste finds itself after it's been disposed of in the environment. Okay, so hopefully that answers the chat question, and I'm taking it that there are maybe no further questions for now. Excellent.
And if there are no further questions, I want to thank you, Margaret. It's really nice to have, first of all, the theoretical background, and then to see it put into the practice. So, a great lecture. Thank you very much.
Thank you.
And maybe you can remind us of what is on next week. I can't recall.
Next week, we have Professor Ji from Nanjing, and then there will be Huan Zhong, also from Nanjing, the following week. So I think it's a mercury lecture, and it's also an earthworm remediation lecture. And the following week, the last of the remediation section, we have Lina Ma, and thereafter we move to the final section, which is the risk assessment, and 3 lectures on that. Okay. Thank you very much, and see you soon, and I'll log out for now.